Hello and welcome to the Real-Time Systems Development module. By now you should all have received the book. Everything you need to know about the module is in here. But before I discuss this in more detail, who am I? My name is Eric Goodyear. I'm a part-time lecturer at De Montfort. I actually spend most of my time designing and developing real-time industrial and laboratory instrumentation. How do you contact me? Well, please do that via email. My email address is De Montfort University, eg@dmu.ac.uk. Now, please take a note of that because you're going to need that information. Because in the book, if you open the book, you'll have to find this yourself. After all of the lectures, you will find a whole series of tutorial questions, and it's absolutely essential that you work your way through these tutorial questions. Now, it's not compulsory, but you're strongly advised to do it. Associated with each of the lectures, there are a set of tutorial questions. Now, what I'd like you to do is to work your way through them, email to me your solutions, and then I will mark them and I will return them back to you. So it's essential that you do all at least send me one email as soon as possible to my email address, eg@dmu.ac.uk, so I can set up an account for you on my PC where I'll keep your work and your marked work. Now, I've said the tutorial questions are not compulsory. You ought to do them. But at the end of the tutorial questions, there is in fact a very, very short sheet that lists the key tutorial questions. The actual title of it is Shorter List of Key Tutorial Questions. These are compulsory. You must do these questions. It's only about 1/10 of the total questions. But these particular questions cover the main aspects of the module. And what I want you to do after each lecture, work through the tutorial sheets. You must do these questions. Email me your answers. I will mark them and return them to you. And the idea is, by the time I get out to you in KL, we will have completed the whole of the module. Complete. No new material will have to be presented to you. And we can use the time I'm out with you for a far more relaxed session of tutorials, chatting, talking around the course, helping you with the coursework in a more practical manner. Let's now move on to the course itself. What is a real-time system? Have any of you any idea as to what a real-time system is? Let's start with something that's going to be a little bit exciting, just to liven everybody up. What is it? Any thoughts as to what it is? Let's just take it off. This is a very simple system. This in fact is a computer. And if you look very carefully at what the dial is, you'll be able to see, in fact, this is a humble domestic shower. That's all. It's just a domestic shower. But why is it a real-time system? It is computer controlled. Here we have the computer processor card that drives this system, and here we have at the heart of the controller a PIC microcontroller. This is the world's largest selling processor. These are sold by the million. They outsell, well, anybody's PC. PCs aren't really real computers. They're very slow things. This is a real computer. Why is it real time? Well, when you go to a shower, you put your hand on the control dial and you turn the dial, you expect something to change. When? Not when the printer's ready, not when the window is closed down, not when the Ethernet queue is cleared on the network. When you turn the dial, you expect the temperature to change now. That's real time. If you change the force that you want the water jet to come out at, you don't want that request queued somewhere in a stack while somebody else who's got a higher privilege to you on the computer system decides whether to service your request. You expect it to happen now. That is a real-time system. Let's look at some other examples of real-time systems. There are quite a few here. This is quite an interesting little unit. This is the engine management unit of a car. Quite an expensive car. Sells for in excess of £50,000, so it might give you an idea as to whose car this is in. Here we have a microcontroller, high-speed computer, its data memory area, and a whole load of input signals monitoring events and information. This comes from the wiring harness of the vehicle. I've just cut it out of the car. This comes from the wiring harness of the vehicle. It monitors the driver controls, the speed of the car, the tacho, how much fuel there is. Everything you need to know about the car will be monitored by this computer, and it will take decisions, and it will drive output signals going off to the driver's panel. There's some relays here. These will be controlling or switching solenoids. We'll talk about these later on, how they work, how the computer controls them. These are switching signals to different parts of the car. Perhaps it's injecting the fuel into the fuel injection system, squirt, 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 or it's applying the brakes, or it's pulling it off for ABS, or it's an anti-skid system. But it's computer controlled. Now, why is that a real-time system? Think about it. You're driving along, happily driving along the road, and you put your foot on the brake. You've got to stop. When do you want to stop? You don't want to stop when the window is closed down and issued a command, it's gone to the stack and into the queue and over the network, and then finally something appears. When you press the brake of your car, you want it to stop now, or within 100 milliseconds. That is a real-time system, because what we're trying to do with the computer is to mimic real-time operations in real life. When you want something to happen now, you expect it to happen now, not sometime later. You won't find a mouse, a screen, a keyboard in a car, but you'll certainly find lots of computers in the car running in real time over local area networks, and we'll discuss that too, because now all modern vehicles have local area networks as part of the harness system, controlling your car instantaneously, or as near instantaneously as a computer can manage. That's a real-time system. Something a little bit more mundane than a nice exciting car. What do we hear? This particular unit is the controller unit for a domestic gas cooker. Why does that need a computer? Well, cookers are very, very complex units. Think about it. You've got a whole array of operators' panels, 4 hobs to control, each with different heats and temperatures, 2 ovens to control, a grill to control. You can't have the grill on and the oven at the same time. You've got to have one or the other, so it has to be some form of interlock. You have to keep the things lit. You have to spark an ignition spark at regular intervals. You have to monitor that the temperature is at the correct temperature and control the level of the temperature in the oven. You have to make sure things are safe. You have to make sure you're not leaking gas everywhere. And you've got to do all sorts of wonderful, clever things. So you want to go out, but you want your chicken to start cooking at 2:30 in the afternoon and for the oven to switch off at 4:30. Well, old-fashioned gas cookers couldn't do that. You will need a modern microcontroller, a real-time system to perform that operation. So here we have a computer in your gas cooker. Another automotive product. This is quite an interesting product. This actual product here is a tachograph from a lorry, and its role is, as well as the small microcontroller that we have, there is a large amount of battery-backed memory here. And what this particular unit does is that it stores 24 hours worth of driving, the complete profile of the car. How fast were you going? Were you accelerating too fast? Were you speeding? Did you leave the lorry running, idling, wasting petrol, generating exhaust fumes? How often did the side lights come on or go off? How often did you raise a particular solenoid? If it was a pickup truck, you could be raising a particular lift unit up or down. It will log all that. In fact, it will log an amazing amount of data. even if you have a smash up, it stores in here the whole velocity profile of the last 30 seconds of your driving up to the point where an impact occurred and the car was smashed up. The police in Europe can, it's actually a legal requirement. One of these must be fitted to every lorry, and they can just pull you over and investigate it at any time they like. And they have to keep records of everything you did from the moment you switched on the lorry to the moment you switched it off. And you require a real-time system embedded in the vehicle to perform that operation. It's very similar to the black box flight recorder of an aircraft. It's statutory now to have these on large lorries, and in fact it's becoming more and more standard to fit these on ordinary vehicles. So we're going to see little miniature controllers such as this in probably all our vehicles in a number of years, storing what's going on. Everything I've shown you up to now has been something that controls something else, but this is quite an interesting little beast. This is a embedded system. It's an infrared thermometer. It reads in the light output in the infrared spectrum from a source, a body, by viewing it with an optical sensor, and basic science tells us that the spectrum of infrared is directly related to the temperature of the body. So you can use this for remotely sensing the temperature of extremely hot bodies. Up to about 1300, 1400 degrees Celsius this will operate. What's really nice about it though, despite all this electronics here, the whole thing takes only 20 milliamps, which means it can run off a battery. So you can take your real-time system monitoring the temperature all the time, and you can put it in your harsh environment well away from you. You don't want to be anywhere near something that's that hot, but you can put the remote electronics there and it will transmit over a 2-wire transmitter to you the latest temperature information. And what's more, it will do all the corrections and maths for you as well, because you can get the most incredible amount of power, processing power, out of these devices, out of these small microcontrollers, and it's doing it in real time. That is a real-time system. Last unit I'm going to show you, we're going to come back to. It's another domestic shower. Now don't yawn about this. It's quite a complex beast, and what we'll be doing over the next few weeks is we'll be taking it to pieces and we'll be looking at individual parts of this shower unit. You can see there's a lot of electronics in here, and embedded right at the heart of it, behind that board, is the actual microcontroller that controls the shower. And I have to tell you, in the 15 years I've been developing control systems, this domestic shower was one of the most complex problems I have ever faced. So we're going to look at how we solve the problem. So here we have before us a whole array of real-time systems. Domestic showers, 2 types of domestic shower. This particular shower unit, the first one I showed you, managed to control this AC mains, a main supply motor, using an itsy bitsy little controller such as this processor. How did that processor control the mains motor to change the speed at which this rotated? Phase modulation, and we'll be discussing that later on. The cooker, very simple system, but don't forget, a domestic cooker can kill people. It's gas, it's fire. Over 50% of the code in this processor is devoted purely to integrity and self-checking of the cooker to make sure it's not gone out of control and not created a hazard in the home. We'll be looking at that as well. Data logging, data tracking in the vehicle. How did this measure velocity and acceleration and log it? How does the engine management system, a little 5-volt microcontroller, control the electrics in the car? A car has a 12 or 24 volt battery. So how can an ordinary computer control systems that run off higher voltages, higher powers? We'll look at that. Simple signal processing. This is the last one, and we'll look at some signal processing techniques towards the end. So we have here an array of simple instrumentation, but they're all computers and not a mouse to be seen. No keyboards, no screens, no mice, no cues, no lands, no delays, no wasted time, because these are real-time systems. When you want something to happen, you expect it to happen now, not tomorrow. That's the key to real-time systems. So, let's just clear the decks a bit, and we'll start with Lecture 1, Data Acquisition, in a little bit more detail. Before we move on to that, I want to draw you a picture. What is your image of a real-time system? I'm going to give you my image of what a real-time system is. What's it all about? We'll start with something very simple. The world, everything, us, our environment, our car, our cooker, our shower, us, our environment. This is what we're interested in. This is what real-time systems are for. They're trying to control and maintain our environment where we live. How do we do this? These things called measurands are quite important. What is a measurand? Measurements we take from the outside world. Examples: pressure, temperature, velocity, acceleration, weight, mass, size, volume. All these things are measurements. In order for our real-time system to do things to the real world, we need to know what is happening in the real world. We need to extract information from the real world, these are our measurands, and get them into our computer. Once we've got it into our microcomputer, we need to process that information, take decisions on it, decide what to do, and then act on the outside world to try and drive it back to our ideal solution, our ideal position, the temperature we want, the time we want the chicken to cook, the velocity we want the car to go. It's a continuous, real process. Measure what's going on. Think about it. Is it right? Is it wrong? Take a decision on what to do, and then try and impact on the world to drive it back to our desired system. Now keep this picture in your mind for the whole of this module, because we're going to delve into each of these sections a bit at a time and discuss them all in detail. Let us start with our measurands. In order for computers are stupid. I'll come back to this concept many times. Computers are stupid. They don't think like we do. They can't perceive temperature, pressure, velocity, acceleration. Remember this, they are stupid. We have to tell them what to do. They do understand numbers. How do we convert our measurands in the real world into numbers? Well, we achieve that with a variety of devices, an important family of devices known as transducers. They are very important devices, transducers. We're going to spend some time just discussing those now. A transducer is a gadget, a thing, a box that converts one measurand into another. It's not a number yet, it's still no good for the computer, but a transducer takes one measurand and turns it into another. Let's look at some examples, each of them here. Any thoughts as to what this is? It in fact is the fuel gauge from a car. The fuel gauge from a car. And look here, we have a float mechanism. Turn it round. There's a float. As the fuel level rises, the float rises, and so it transduces volume into an angular rotation. Here's the angular rotation, there's the volume. Now all it's doing is transducing one measurand into another measurand. As the fuel increases, we've transduced level or volume into angular rotation. Simple transducer. Let's look at another very simple transducer. The difference between the fuel gauge, which costs about £2 or £3, and the oil gauge I'm opening up now is that this costs about £200. And it is a bulk flow transducer. We're going to look very carefully at how it works. Because again, most transducers in fact are quite elegant and simple. But this measures the fuel flow, it's the oil flow in a truck. Assuming I'm moving it the right way around. Now, just going to work. As the fuel flows through the system, so these dials will let small quantities of the fuel pass through in a circular motion. Every time there is a circular motion, a pocket of fuel is trapped into this little chamber, and as the dials turn around, eventually that fuel will flow through from the inlet to the outlet. So here we have the fuel comes in, it's trapped in the pocket, and then it will flow through to the outlet. So what happens is as the fuel is flowing, we have this continual circular motion. Firstly, the valve opens, fuel will flow into this chamber here, and then it seals off the inlet, and fuel will then flow out the other side. Now if it's not too clear, don't worry, I'll be bringing this with me and we'll be able to see it in operation. But hopefully what we can see is that as the fuel flows through, we have a continual rotation motion. In this position we've trapped our little pocket of fuel. Now it's just been released through and can now escape out. This is a bit of precision mechanics. The amount of volume of fuel that is trapped in that area is a precise quantity. Therefore, if we count the number of rotations, we know exactly how much fuel has passed through the pipe into our system. What have we done with this particular unit? Well, we have transduced flow rate into angular motion, a circle. Every rotation is a precise quantity of volume of fuel, absolutely constant. Now, what we can't see, I'll just take out this little slug here and we'll move into it very carefully. Just there, that is a magnet, a permanent bar magnet. So what happens is that if we have a pickup like an electric guitar, that's all it is, every time that rotates, we have a magnetic sensor, in fact it's embedded inside, a magnetic sensor there, we can detect when that magnet flies past. So what we've managed to do is we've transduced flow rate into units of volume, into rotation, into a changing magnetic field, and if we have a simple guitar pickup here, what we're going to get out is we will receive along out of the transducer, as it rotates, hopefully a nice, won't be that perfect, pulse train. Every time the magnet passes our pickup, we'll get a pulse. So in order for our computer to determine the volume of flow, all it has to do is to count the pulses. Here we have a transducer. What is a transducer? It converts one measurand into another measurand. That's its role. I'll give you some more firmer rules later on. Well, let's just look at a few more transducers. I've got all sorts of gadgets here. Here we have another fuel gauge. Another very simple concept. In fact, this is simpler and cheaper. This one actually, this rather complex one, came off of a Ford car. This one came off of a far more expensive sports car, and they spent about half as much money on it, which tells you a lot about what you're buying when you buy an expensive sports car. Very, very simple mechanism. If the document scanner is capable of showing it, we'd like to come into the hole. We may not be able to see directly into the hole, but let's try. Right, you might be able to just see here there is what looks like a little metal wiper, and as we rotate, this isn't actually an electronic component. In fact, it's a variable resistor. And the idea is that as we change the position of the angular motion, so we will change the point at where we pick up off of that resistor, and thereby what we have done is transduced volume to level to angular rotation to a variable resistance within the electronic circuit, and now we're getting something electrical. That's important. We'll come back to why things need to be electrical. What else have we got here? We've got all sorts of exciting things. This is quite useful, and I talked earlier on about crashes. This is a crash switch. You might be able to view it here. If we look down on it, there is here a small ball bearing that is sitting in a cup. Now, this is a dynamic thing. Up there at the top of it, there are some circuit breakers just there, and the idea is when the ball falls out, we'll do it. I've got there's the spring mechanism. When the ball at the moment is at the bottom, it's held in by a magnet. If sufficient force impacts on this to release that ball, it will hit that switch, and it's now primed that, and that's now permanently locked open. We'll do that again. Push it in. So that's now loose. You can see that's loose. That's actually in the off position. Give it an impact, and now that's locked open. What role does that play? Well, this is used to detect when an impact is incurred on a vehicle, and the first thing it does is it cuts off the fuel pump, cuts off the engine, and tries to make the car safe, releases the airbag. Very, very simple transducer. It's transducing, in fact, force, that's the impact, into a contact closure. Still a transducer because it's turning one measurand into another. Oh, more of these. Now, we're going to come back to these later on as well. This just looks like a big lump of metal, doesn't it? Yeah, there we have a cylinder, a cavity. Here's a cavity, totally void in there, and just a lump of metal. What on earth could that be? What could it be? Well, in fact, this is a pressure sensor. A pressure sensor. How does it work? Well, it works in a very simple bellows arrangement, except it's done in very thick steel. But think about a small bellows. If you had a little cavity and a bellows such as this, and there's our screw thread, and we apply a pressure into the bellows arrangement. Now, if this was a nice soft material, I'm sure you'll agree, as the thing blows out, it will move and we will get a displacement. So a bellows is in fact a transducer that will convert pressure into linear displacement. That is a transducer. Very simple concept. I'm sure you can say that. You can take a balloon, blow up the balloon, And the more the pressure, the bigger the balloon, because the balloon is converting pressure into linear displacement. If you do that with an enormous thick piece of steel, the rules are still the same. This is a bellows, but it measures extremely high pressures, and it's used in furnaces and process control. Same concept. We're converting one measurand into another measurand. This also is another pressure sensor. I'll leave the bellows arrangement up there because this is still true. But what's interesting is that instead of having at one extreme this enormous piece of metal doing the job, this is done in silicon. Here's the actual bending member here. This is actually etched onto silicon. And when pressure is applied to this ceramic by pushing down onto the paper, that moves the bellows arrangement, which has been etched into, you can probably see some of the microcircuitry in there, and in here is all the signal conditioning required to convert that pressure into an electrical signal that is transmitted out. And here we can see the electrical contacts where you'll connect that off. They all work on the same mechanism. It's basically pressure is converted into a linear displacement. This is going to measure extremely small pressures because it's very small movements in the ceramic will be detected, whereas this is measuring very high pressures. Very simple concept. But what are we doing? We're just converting one measurand into another. Pressure to linear displacement. What else have I got in my box? Oh, more crash sensors, more pressure sensors. Oh, we've got nothing else exciting here. Oh, here's a simple one. What's that? This is the smoke detector. Again, a transducer, because it detects particles, particle counting, because that's how you detect smoke. Very small particles are generated when something's on fire. These get into the actual smoke detector itself. The particles will penetrate into the grill, and in here there is a very, very small here's the holes where the particles will enter, and in here there's a small radioactive source. That's how they work. Very, very low radioactive layer. But as soon as the particle gets in there, it's ionized and a current will flow between the various electrodes, and thus we have the simple domestic smoke alarm. But again, it's a transducer because it is converting particle size into electrical current. Well, if we leave the transducers to one side for now, let's just run through what we've learned so far. Let's go back to our picture. Here we have the world. In order to control the world, we need to know what's happening in it. To do that, we need to take measurands out of it. What are measurands? Pressure, temperature, flow, velocity, speed. You can name them yourself. You should be able to write down a whole range of measurands that you require to measure. We use tools known as transducers. Here's our transducers to convert measurands into other measurands. Now, what's the main rule about a transducer? What's a measurand? A measurand is a property, a phenomena in the real world that we can measure. That's why it's called a measurand. The role of a transducer is to convert one measurand into another measurand. But it's not as simple as that. There must be a known relationship between the input measurand and the output measurand. In here, clearly, the angle is directly related to the level. And so it's true for all of these transducers. The amount of displacement is directly related to the amount of pressure. We must be able to write down the equation that relates one measurand to the other. Why? We're going to end up in a computer sooner or later, and it's got to do some thinking and number crunching. So we need to know what it is we're measuring. So a measurand, a transducer converts one measurand into another, and there must be a known mathematical relationship between the two. Still not the whole story though, because even though we've gone from level to rotation, that's still not good enough. ultimately we're trying to get out an electrical signal, because electrical signals can be turned into numbers which we can get into our computer. So what have we got here? There is resistance. By moving this bellows in and out, in fact, we are creating an electrical component known as a capacitor. A capacitor, this is the electrical symbol of a capacitor. It's two metal plates. And what a capacitor does is it stores electricity. The closer the plates are together, so the amount it can store will vary and increase. In fact, a battery, an ordinary household battery, is just an extremely large capacitor that's been charged up with a lot of energy, that's all. Now, if we move or change the distance the plates are apart, so the electrical property known as the capacitance of that varies. If it's electrical, we can get it into our computer, and I'll show you how shortly. So that gives us capacitance. This little particle device gave us a flow of current. The sensor, this in fact wasn't an analog, wasn't a variable signal, it was either off or on. So it's a pulsed output, a frequency. This very expensive bulk flow sensor, £200 worth this is here, this gave us a frequency as well. As that rotated, so we got a series of pulses would flow out as it rotates. Pulse, 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 pulse. As that wheel rotates, we get a pulse train. So what are we trying to do? We are trying to convert our original measure and what we wanted to measure into an electrical signal, an electrical output. This is the key. Now, in the notes there are a variety of interesting devices, and I want to discuss in detail just a few of them. The linear voltage differential transformer is an extremely important device, very, very widely used. How does it work? It uses magnetism. If we have a coil, pair of coils, and a secondary coil, we don't need to do much physics for this. In fact, don't worry about if the physics is beyond you. I'm not going to examine you on that. I just want to show you briefly how they work out of interest. If we have a pair of coils balanced on either side, primary with a secondary, and we put in the middle of it a ferrite core, a bit of iron or some form of ferrous material, then physics tells us that when that is dead central, when a current is flowing through the primary, we will get induced into the secondary equal and opposite currents, and we will get zero out in terms of current. But if our ferrite shaft, here we have our ferrite shaft, was to move one way or the other off center, there'd be an imbalance. And it can be shown that the change of current output on the secondary is directly proportional to the position of the inner core. So precise is this mechanism that LVDTs can measure movement less than a micron, less than a millionth of a meter. They're incredibly sensitive devices, very, very widely used. Electromagnetism, in fact, is a wonderful technique. This particular sensor we saw earlier, this sensor uses electromagnetism. Very, very nice technique because it's so sensitive. And the LVDT is one of the classic use of electromagnetism to measure linear displacement. It's all in the notes, please read it up. There's a discussion on the pressure cell. There's a discussion on the level sensor, but I want to turn to the picture on the flow rate meter, because that again is an example of a very, very simple system. I mean, this particular level gauge, that will give us an analog, a variable voltage out. So that's one type of electrical signal. It is varying current or a varying voltage that must be directly related to the input signal. The other mechanism is where you get a pulse train. So let's consider a very, very simple flow meter. And let's assume there's some water and this is flowing along. How can we measure the flow rate of that water? Well, if we were to put a very simple turbine, a paddle wheel there, as that rotates, water is flowing, it rotates the paddle, and we will get a pulse train coming out that is directly proportional to the rate, the flow of water. I've actually got a flow meter here. We'll make some room. I'll be a bit more generous with my £200 worth of sensor. I won't fling that in the box. I'll put it to one side. But I'm going to go back to my shower system. We're going to start pulling the shower system to pieces, and we'll look at one very small part of it. Here we have the water inlet comes in through this piping system, through this sensor here. This in fact is the solenoid, and we'll look at that later. This is what controls the amount of water flowing through. This is the transducer that measures the flow rate. That's what we're going to look at closely in a minute. And then finally the water goes through the heating element and comes out of the shower system, and eventually it comes up, 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 and will flow down your head, hopefully nice and hot at the right speed. Let's just look at this a little bit closely. Pull it to pieces carefully, and we'll just get out the central core sensing and control element, a bit like surgery this. Just put it there for a moment, and we'll come over and we'll look at that in a little bit more detail. Now what we have on the scanner at the moment is the solenoid unit and the transducer. It's just the transducer I want to get out for now, except I haven't got my tool. Slight pause while we find the screwdriver. Right, we're just making the incision into the transducer. Remember, this is measuring the flow of water. Now we can home in on we can see that we have here a very small paddle wheel. As the water flows, it rotates this paddle wheel. Let's just take that out. And there we can see the vanes of the paddle wheel. It's just like a little watermill, isn't it? And as the water flows, so this will rotate. So here we have an extremely low cost and effective flow rate sensor, paddle wheel. Now, how does this work? Well, this material here is a ferrite material. So what we require, if we have our paddle wheel, rotating. These are ferrite materials. If we were to place above it an electromagnetic sensor that goes off to our computer, what we would have coming out of our sensor is a pulse train every time one of the vanes of the wheel rotates. So if we can count the pulses into our computer, we will know exactly how much water is flowing through our shower system. Now, there's a special name for this type of sensor. And it's known as a Hall effect sensor. Hall effect sensor. You'll come across this name if ever you go through a transducer book. You'll often come across it. It is the standard, reasonable quality, low cost electromagnetic pickup for detecting changes in magnetism. What it's used for is a variety of things, but ultimately it gives us a pulse train which we can get into a computer. Why is that good for us? Well, computers are fundamentally stupid, but they are capable of counting. And if they can count pulses, so we can measure flow. Even better if they can time them. So we say how many pulses in 100 milliseconds, we can measure the flow rate. So there is another sensor unit. This has come straight out of our shower. Our little turbine meter with a Hall effect sensor will give us a pulse train that can go into our computer. So what are the rules here? What are the rules? Measurands, things in the real world. We need to convert them into other measurands using transducers till ultimately we will get out of it an electrical signal, a voltage or a pulse train. There must be a known absolute mathematical relationship between the actual input value and the output value. So each pulse, we must be able to relate that to an absolute measurement, because ultimately the computer mustn't work in fairyland. It's got to work on real numbers. It needs to know the pressure was such and such, or the temperature was such and such. So where are we so far? The world has got measurands in it. We take information out of the world using transducers, and then we get that information into our computer. But how? I haven't gone into that yet. The bulk of our transducers will give us a variable electrical signal. It'll be a changing voltage or capacitance or resistance, whatever it is. Ultimately, that can be turned into a variable voltage level. So how do we get our voltage into our computer? Well, the next session now, we'll start discussing a family of devices known as analog to digital converters. ADCs are analog to digital converters. What are they? They're little tools that convert an analog, a variable voltage, into a number that the computer can understand. And here's one. The computer is there, but this device is the analog to digital converter. It can handle up to 8 different independent analog channels, variable voltages, and converts them into numbers that our computer system can understand and take decisions on. That is an ADC. You need to know about ADCs. You need to know about the different types, how they work, how to write programs to control them, and that is a key part of this module. So let's run through them. I'm going to introduce to you a variety of different types of ADC, but let's just consider one of the simplest. And the simplest device you can get is known as a dual slope ADC. Now, how does it work? Well, it works on the principle that if you have a capacitor, you can charge it up. Now, what am I talking about? Let's get something you might understand. When your car doesn't start in the morning, the most likely probability is the battery's flat. What do? You go and get a battery charger and charge the battery back up. The more flat the battery was, the longer you've got to charge it. If you want to charge it quickly, you have to apply a much higher charging voltage to the battery to get it to charge quicker. There's a direct relationship between how quickly you can get voltage into your battery to get your car going and how much volts you're trying to apply to it in the first place. The greater the charging voltage, the quicker it will charge up. Now, a battery is no more than an extremely large-scale version of the humble electronic component known as a capacitor. And the whole basis of a dual slope ADC is it relies on this phenomena that you charge up capacitors, just like batteries. So how does a dual slope work? Well, let me draw a graph. First of all, here's our capacitor. We don't need to know about the electronics, but we apply our unknown voltage to the capacitor, and slowly what happens is the charge on that capacitor will slowly increase until it matches the input voltage. That's the idea. If you apply a very, very low voltage, it will charge very slowly. If you apply a medium voltage, it will charge a bit quicker. If you apply a very high voltage, it will charge very quickly. So the actual slope, the rate of charging, is directly dependent upon our unknown voltage. We don't know what the input voltage is, but what we could do is charge it for a known period of time. Whatever the voltage is, we will charge it for a known period of time. That's very easy for a computer to do. You can do it with a program loop or a bit of timing. We just say we're going to switch on the unknown voltage and we'll let it charge for, say, 1 second. Now we switch onto the capacitor a reference voltage, a known reference voltage, and what will happen is the thing will start discharging. But if this is a constant, the reference is a constant, they will always discharge at the same rate. So the discharge patterns are always parallel lines. And so now we will get different discharge times depending upon how great it was charged up in the first place. And there is a direct relationship between the two. V unknown divided by T must equal V ref divided by our unknown time here. It's a direct linear relationship. So using an extremely simple, low-cost electronic component, they cost less than a penny, a capacitor, and a little bit of logic in your computer, you can implement your own dual slope ADC extremely easy under program control. How does it work? First, we charge up our unknown voltage for a fixed period of time. Then we discharge it with a known reference and measure how long it takes. And computers are very good at that. They can time things very easily. You simply use a programmable timer, and we'll look at those later on. So the dual slope ADC, very simple, very low cost. Now let's think about some of its characteristics. That's how it works. In terms of speed, it's very, very slow. This is our dual slope. Start doing a table. In terms of speed, it is very slow. Cost, it's a very low cost system. Quite good, that's why they're widely used. In terms of noise immunity, it's very, very good. Why do I mean that? Why should that be? Well, let's just consider the graph. If there was some noise on our system, noise normally comes in general as a high frequency interference. If there's some noise on our input signal, the effect of that noise is that it will be cancelled out, it's averaged out. Because we're charging up, let's look at this in finer detail. And here's our noise, and we're charging up our capacitor. The positive bit of noise will tend to cancel out the negative bits of noise. So overall, as long as you charge for a long period of time, you make that time quite long. And typically, you would do that as 1 hertz to 10 hertz. So you do maybe 10 conversions a second, 30 at the most, maximum, but typically a few conversions a second. Then the noise tends to get cancelled out. So we have a ADC that's slow, typically 1 hertz to say, I'd say 1 hertz to say 30 hertz maximum. Cost is low, it's quite cheap. Very good noise immunity. What if we need to go faster? I mean, that's going to do for most simple domestic systems. It's not going to work for a car. You need something that's a bit faster than that. So the next type of ADC that you need to consider is a device known as a successive approximation. Successive approximation. Now, this exploits the fact that computers work in binary numbers. And so let's think about how a number is quantized. I can't do too many bits. Let's assume we're going to have a 3-bit system. If you had only 3 bits, you would have 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. And to make my life simpler, let's assume that the full scale voltage is 8 volts. And this goes from 0 volts to 8 volts. And we've got quantization errors. Any value between 0 and 1 is 0 to 1 volt. That's 1 to 2 volts, 2 to 3 volts, 3 to 4 volts, 4 to 5, 5 to 6, 6 to 7, and 7 to 8. So these are our various levels. The most significant bit here means 4 volts. The next bit means 2 volts. The next bit means 1 volt. They're halving each time. Pure binary progression. So the way that we use an SAR is that we try out each of our voltages in turn, from the most significant down to the least significant. So firstly, here's our 4 volt, our 2 volt and our 1 volt. We put some switches on them and we just add them all together and take them into some sort of electronic circuit. And then we have our unknown voltage comes in as well. And there's our answer. We try each one in turn. So first we try 4 volts. So we close the 4 volt switch, we apply 4 volts. Let's assume our unknown voltage was 6.5 volts. And we say, right, was that greater than or less than? If it was greater than, we leave the switch permanently closed and we set the most significant bit to 1. Now we close the next switch. So we close that switch and we say, right, we've now got 4 plus 2. Was that greater than or less than? Very simple decisions. Computers like simple decisions. Well, 4 plus 2 is 6. It's less than 6.5, so that will remain on. So we leave that switch permanently closed and that closed. Now we try the last switch. We close that and we say, was that greater than or was it less than? Well, now we've got 4 plus 2 plus 1 is 7. It's greater than. We've gone too far, so we open the switch again and we get a 0. So the result of this successive approximation is 1, 1, 0. It's a very simple concept. The idea is here's our unknown voltage, and we try out different values in turn, going down in the binary pattern from a reference. We first try 8 volts, 4 volts, 2 volts. And then if you want more precision, 1 volt, half a volt, quarter volt, eighth of a volt, and so on and so on. The more tests you do, the greater the precision of the conversion and the better and more accurate is your result. Successive approximation is the technique of trying out a series of possible trial voltages in a binary changing mode, smaller and smaller binary divisions of the reference voltage. What's nice about these things is that they are much faster. So if we now go back to our table, we have an SAR, and now we'll say that they are fast, typically 1 kilohertz to, oh yes, I've seen them at 100 kilohertz, but tens of kilohertz. They can go much, much faster, and so they're very widely used in process control and industry. The cost is a medium cost. I ought to put some numbers on these. I'd say you're looking at maybe £1 to £5 there. So that's $6 to $30. Medium cost, typically £5 to £20. So we're talking at $30 to $120 there. And in terms of noise, unfortunately, they're rather poor. They're very poor. Now the reason is that if you were halfway through the conversion and suddenly a noise spike came in, then that's going to disrupt the whole of the reading and you get rubbish. So they're very, very poor in noise, and you have to apply some post-processing, some digital signal processing, that's lecture 8, to extract the noise and get the good information back again. So here we have our successive approximation, fast, medium cost, but very poor in noise. However, what if we need to go really, really fast? Well, what we could do, the successive approximation idea had a single comparator. And that comparator, you tried the different voltages out on as you tried to successively approximate to the answer. The alternative is to just go right to the other extreme. And instead, you have a circuit where instead of one comparator, you have hundreds of comparators, literally. And you bring in our unknown voltage, goes to everyone simultaneously. And instead of varying the trial voltage on them, these are fixed. Every one of these is fixed, and there is a comparator for every possible solution. I'm drawing 6, as typically these come in blocks of 6. So this would be 64. Oh, sorry, rather 63, 62, 61, 60. This is the binary answer, 59, all the way down to 0. So what we do is that instead of trying out lots of different values, they're all there immediately. Every possible solution is present simultaneously. We apply our unknown voltage, and instantaneously, or pretty quick anyway, you have the answer. Needless to say, these things are very expensive. So a flash ADC is very fast, 10 kilohertz to megahertz, extremely fast, very high cost. I'd say typically £50 plus. You know, you can pay hundreds of pounds for these, so you're into thousands of dollars for these things. The noise immunity, surprisingly enough, is good. The reason they're good is that the flash ADC is going to go faster than the noise. So all that will happen is it won't disturb the answer. You'll actually convert the noise, and you'll get it as a real number reading in your data stream. Who uses them? Well, obviously the military use them. That's who they were developed for very high-speed systems. But also, you use them in video, because video data rates are in megahertz, and all video channels require megahertz data transitions. So flash ADCs are widely used for very high-speed multimedia and video systems. So those are the 3 main key ADCs. I need you to know the difference between them and to discuss how they operate with respect to each other in terms of speed, cost, and noise immunity. One last one, though, we ought to just discuss that's coming on the market recently. It's actually an idea been around a long time, but is only really being marketed in the last few years. It's a device known as a Sigma Delta ADC. And the way it works is that it's based on having a counter, normally 24 bits long, and the whole of that counter is applied through another device called a digital to analog converter. This is a device that turns numbers into voltages, and we'll look at those in the next lecture, and that is applied and compared to our unknown reference. And that is fed back into the Sigma Delta counter. So if it's the output of the comparator, either 1 or 0. If it's 1, then the device will count up. If it's a 0, it will count down. So the idea is this continuous loop going on, and the idea is that the 24-bit number is trying to track the voltage, the unknown voltage as it comes in. So what happens is, here's our unknown voltage, and our counter will be down here. And go until it finally matches. And then, as the unknown moves up and down, our counter will track it and follow it, tracking and holding, using this up-down technique. Now, you might think that's incredibly fast. In fact, once it's locked on, it is actually extremely fast. The problem is that if there's a sudden change in the unknown, like you've just started and switched the thing on, it takes a long time for the thing to finally count up and track it. Once it's got it, it holds on to it. But if it's knocked off, it has to click down or click up. There's no instant changes with it. So the end result is that even though once it has tracked and held onto it, it is quite good. In fact, and we'll give it its proper title, sigma delta. It is in fact deemed to be very slow because there are some circumstances when it will take a long time to do the conversion. The reason that it's popular is that they cost less than £1, less than $6. They're very, very, very cheap devices, and that's why they're becoming very popular in some domestic appliances. And their noise immunity is good. Why? Because the noise is so fast it won't even see it. They're so slow to respond that the noise will be in and out and gone before you even know and anything has happened. So there's our full panoply of ADCs. So let's think of our picture now. We started with the world, and we filled in a little bit more information now. We've extracted our measurands. Using transducers, we finally got out some electrical signal. Now, if that was a voltage, we can now put that into our ADC, and out comes a number. And at last, our computer can do something, and it has, through this whole chain of devices, has extracted some knowledge and information about the outside world. It now knows what's going on using these devices, transducers, ADCs, and that's giving us numbers. And what's the rule? There must be a known mathematical relationship between the input measurand and the output measurand. And having got that, we must be able to think of that in an absolute engineering unit. We can't just say the thing is going fast. We need to know how many kilometers per hour or how many liters. It has to be an absolute measurement. That's the key thing. There's the word absolute. Absolute means we know precisely what it is in a known, agreed engineering unit. And now finally we have a number that we can process in our computer. What if it was a frequency though? We dealt with voltages, but a number of our transducers gave us pulsed outputs rather than voltages. How do we cope with those? Well, that's simple. One thing that all computers have available, well, I should say computers, I'm talking about these sort of computers, is that they have as standard digital inputs. What are digital inputs? Well, they're like memory devices, but instead of being embedded in a chip, they come to the outside world, which means you can take directly into the processor information from the outside world. So if you look at the basic guts of a microcontroller, you have the CPU, just as you have in a PC, but also you have code space, you have some RAM, you have a timer, because that is key to all real-time systems, and we'll look at that in more detail later. But the other thing is you always get is I/O. So when you actually look at a particular microcontroller, I'm trying to find one that will show up on the picture. Here's one. The engine management unit of this vehicle, here we have inputs coming into the board. This processor, these pins, in fact 24 of the 40 pins, are memory mapped I/O that can be accessed directly by the CPU, so that we can put voltages onto these input pins and read them directly into our program. Our program can input the state of these digital pins from the outside world simply by accessing these pins, which are memory mapped at fixed memory locations. So all we have to do, we've got a C program, set up a pointer that points to that memory location, and then you can write a program that directly operates on an input signal from the outside world. Very simple to do. So how do we do that? We now know we can feed into our computer digital input signals. How do we calculate speed? Well, here we have a very simple, actually this is one of the transducers I forgot to mention earlier on. This is a puffometer. I'm going to use it for another task in a minute. How does it work? Well, we have here a very simple dial there that can move, and it measures in fact the volume of your lungs. It's a medical instrument, and all you do, you set it to 0 and you go blowing it, and then you give it back to the doctor and they can look at that and see how far you've blown, and that gives you a measure of the capacity of your lungs. Very simple transducers converted volume of lung into linear displacement on the sensor. That's not why I'm going to use it. I'm going to use it as a pretend shaft. Now let's assume I've got this is just a shaft in a piece of machinery, and it's rotating round and round and round and round and round. How do I know how often it has rotated? Well, you might have noticed at this end of it I've put in a little black mark. So there we have black, white, black, white, black, white, black, white. Now all we have to do, every time that rotates, if we count the number of pulses, number of transitions, we know how often we've turned. So here's 0, 1 rotation, 2 rotations, 3 rotations. Very simple. So the rotating shaft will give us, there's our shaft, it's rotating round, and that will give us a pulse train that we can take directly into an I/O pin of our processor, and all we have to do is, if we've got a pointer in our program that accesses that memory location, we can just count the transitions from 0 to 1 and then from 1 to 0, and that tells us how many times it's rotated. But there's a difficulty with this. What happens if I rotate that way once, but then I reverse and I rotate back? Well, in fact, we've gone nowhere at all. But how did we know the difference? We've got no idea. Because having a single sensor, all right, it was okay in this system, in this transducer, we know that things only rotated round once in one direction. We know in our little turbine meter it can only rotate one way. So we just count the pulses in our program. Very, very easy to do. Water wouldn't back up down the pipe. But how can we cope with a rotating shaft, such as in a motor or a machine tool, that could reverse? Well, the solution is to put another mark on. I'll just do that. And now, if we start from rest, we've got 2 marks here, 90 degrees out of phase with each other. Start from rest, and we're just going to look along the center line here, and we have 0, 0. We rotate a little bit, and it goes to 0, 1. Rotate a bit more till we get another change of state. Now we have 1, 1. Keep rotating that direction, we get 1, 0, and now we return back to the start. That was that rotation. You get a totally different pattern, and believe me you do, I'll show you, when you rotate the other way. If we started from 0, 0 and we're rotating in this direction 1, 0, then we go to 1, 1, then we go to 0, 1, and now we're back to our rest position 0, 0. And there's the proof of it. This sequence is totally opposite to that one. It's the reverse sequence, but you will never find the same transitions. 00 goes to 01. In this one, 00 always goes to 10. So by adding the second marker, not only are we able to determine how much it's rotated, we also know what direction it's rotated in as well. And this is known as quadrature encoding. Quadrature encoding is a key technique for controlling machine tools using DC motors, because you need to know not only how far and how fast it's spinning, but also which direction. So there is a simple technique that you need to know about, quadrature encoding. So now let's just summarize the whole of this session. We have the world. Things we want to control, measure, get into the position we want. We extract measurands, pressure, force, temperature, position, linear displacement. Using transducers, we convert one measurand into another measurand. We looked at various transducers. I need you to describe some very simple transducers. There's plenty in the notes and diagrams of how they work. When you go home today, have a look around your home. See if you can spot any transducers in your own house and try and work out how they work. They're very simple things. If they give us a voltage output, we can convert that voltage into a number using an analog to digital converter, an ADC. And we discussed 4 different types of ADC. And you need to understand in outline how each of these work: dual slope, SAR, flash and sigma delta, how they vary in speed, in cost and in noise immunity. Remember the dual slope? It charged up our unknown voltage and then discharged with a reference, and the ratio of the times gives us a measure of the unknown. The SAR, successive approximation. We tried out a variety of voltages, slowly homing in to our unknown voltage. Here's our reference, and we home into it, successively approximating using smaller and smaller differences to get out the value. Our flash ADC, that does an instantaneous conversion of the voltage using lots and lots of comparators. And finally, the very slow sigma delta tracking ADC. So these devices, these will convert voltages into numbers. So that was what we use our ADCs for. But the alternative is we may have had instead a pulse train. So how do we cope with a pulse train? Well, we use a digital I/O, standard concept. The pins on the processor, if we actually have a processor and you look at it carefully, a microcontroller, you won't find this in a PC, you've got to get a real computer, one of these things. And here we have each of these pins here on the actual device. They will take in a digital signal, and these are memory mapped. So you can write a program that accesses these directly. So you can say, right, what is the state of that wire? Is it a 1 or is it a 0? Remember, computers are stupid, so they only know binary, a 1 or a 0. And that is how you read in digital data. And if you've got a timer as well, which is essential, some form of independent real-time clock, and we'll look at those later, then you can time the rate of arrival of these pulses, and that gives you frequency information. So in the case of our turbine meter, here we have our turbine meter that rotated around and around. We could have just counted the pulses to give us volume, but if we time them as well, we know the flow rate. And we're going to use that phenomena to control our very complex electric shower later on in this series. What about direction? If you have 2 pulse trains 90 degrees out of phase with each other, then you have quadrature encoding. So we'll draw that again. Here's our 2 pulse trains 90 degrees out of phase. This gives us both an absolute quantity and a direction, because the binary pattern is always can change in one direction only, and you know the direction you're moving through the pattern, and so you know whether you're moving forward or backwards using quadrature encoding. So that ends this session on data acquisition. Next session we'll move on to how we control the output, some of the output devices, and once we know how to read things in, once we know how to control the outside world, then we can start looking at the programming itself.